So originally I was going to make moonshine for my project, but instead I made glucose. Actually, I did enzymatic hydrolysis of lignocellulosic grass. My research question was the efficiencies, which included glucose created, cost and environmental impact of 3 enzymes in the process of enzymatic hydrolysis of lignocellulosic grass. What is lignocellulosic grass? It basically is plant matter. Anything from the earth that has cell walls is lignocellulosic material. It is the most abundant raw material in the earth. It includes grass, corn or wood chips, corn stalks, tree bark. It is literally everywhere. When you mow your lawn and you throw it away, what if we could turn that into fuel? What is enzymatic hydrolysis? Enzymatic hydrolysis is the process of using specialized enzymes to break down the cell walls in lignocellulosic material to expose the glucose and other sugars that are behind the cell walls. Right now, ethanol fuel is produced from corn and sugarcane. These two are used because they already are in simple sugars. But you could use lignocellulosic material through enzymatic hydrolysis to expose the glucose, and then you could distill that into ethanol fuel. But why use lignocellulosic material? As I said before, it is the most abundant raw material on Earth. Plus, the amount of water it takes to grow, say prairie grass, is so much less than, say, corn or sugarcane. It doesn't even need irrigation. It can grow in rainwater. It can pretty much grow anywhere because the amount of nutrients it needs is almost non-existent. And then when you look at fertilization runoff, non-existent too, because you don't need fertilizer to grow prairie grass. Right now it's cut and thrown away. The enzymes that I used in my experiment were Trichium oryzae, Aspergillus, and Aspergillus niger. The grass I used in my experiment was Miscanthus syngrissimus. I know it sounds complicated, but really it's just a common prairie grass found all over the world. And before using this grass in my experiment, I put it in a food processor and I chopped it up. That way the surface area was more. That way the enzyme and the grass could come in more contact, hopefully producing more glucose. The buffer I used a 2 molar acetate buffer at 5.2 pH. For those who don't know what a buffer is a liquid that resists pH change. It can both neutralize an acid and a base, keeping a liquid at a certain pH. I choose this acetate buffer because it kept the liquid at 5 pH, which increases enzyme activity. Trial 1. So I put the grass, the enzyme, and the grass, enzyme, and buffer in a beaker, and I did 3 enzyme concentrations for each enzyme, making 9 beakers, and then I put in a 40 degrees Celsius water bath for 24 hours. I turned on the water bath 2 hours before the experiment to make sure it was at 40 degrees Celsius. I then put the beakers in and waited 24 hours, as I said before, and then I tested periodically throughout the 24 hours to make sure that the water bath was at 40 degrees Celsius. After 24 hours, I pulled the beakers out, I put them in a 95 degrees Celsius water bath to kill the enzymes, and then I added water because the buffer had evaporated throughout the 24 hours, and I mixed the water in, used a pipette, and then I tested for glucose. $800, 4 hours, and countless hours outside the classroom, more like days, and I failed. I didn't find any glucose in trial 1. The buffer solution evaporated, which was a big issue. The pH went down, and I think it reduced the enzyme activity so much that no glucose was created. Also, the water bath temperature was too inconsistent. It was from 32 degrees to 48 degrees Celsius, and it either could have killed the enzyme or decreased the enzyme activity so much that no glucose was created. And I went to Miss G and I told her, I don't want to do it. I hate enzymes. They're stupid. No one cares about this anyways. But she insisted that I try again because I had all the materials to do it again. So in trial 2, I tried to make it work. So I put parafilm on top of the beakers to prevent evaporation. That way I didn't have to put more water in and the pH would stay at a constant 5. And I also put masses in the beakers to decrease buoyancy. That way I could add more water to the water bath, making that the temperature would stay more consistent. I also turned the water bath on 2 days before the experiment. That way it was precisely at 40 degrees Celsius when I put the beakers in. And literally, I could not run another trial. I ran out of enzymes. And I really wanted this to work because I didn't really want to write a 5,000-word paper on how I failed. And I did it. I found glucose. In trial 2, I found glucose at 21 milligrams per deciliter at 27% Trichium oryzae. This is a picture of the beaker from trial 2, and as you can see, right here, white precipitate on the outside of the beaker, I believe that is glucose. Now, answering my research question that I brought up earlier, Trichoderm marisa was the most efficient enzyme because it was really the only enzyme that created glucose. And while I did not solve the problem of finding renewable fuel, what I did do was I found the efficiencies of these enzymes. And possibly a future scientist, or me, could find, later in my life obviously, I could find out why the Trichoderm marisa was more efficient. I could break down the enzyme, and I could find why it's more efficient, and then I could either engineer or find another enzyme in nature that would make lignocellulosic ethanol fuel relevant in today's world. Now, we possibly could solve the problem of finding a renewable fuel source, and it's growing in our front lawns. Thank you.